Okay, I'm going to go through this last module here in fire alarms, wiring procedures. So this is going to be more applicable to our lab that we're going to do. We'll go through, it does kind of revisit a lot of the things we talked about earlier, so I won't touch on some of the stuff in depth because it was in the previous module. But in the beginning of the module, they just talk about the conductors, the wiring methods. It's all code stuff, so definitely go through that. They start talking about FAS cables, so you can have unshielded, shielded, or an armored. So these are fire alarm cable that we commonly will see in fire alarm installation, so fire alarm and signal cables. So it's just good to have a look at these and see exactly what they look like in case you've ever come across them. The electrical supervision part of it, again, this is through the code, and it's saying that each conductor within a fire alarm system be independently terminated so the electrical supervision circuitry works correctly. So what they're getting at is if I have it terminated like this without a splice like here, if that device gets removed, I now have an open in my circuit. So then my panel's going to know there's an issue and it's going to go into trouble because it's not going to have a complete path through that, potentially through the end of line resistor, or depending on, I guess, whether it's a class A or class B. But we might not ever want to do this. There are some instances I'll talk about where this is allowed, but it's a very specific instance. Okay. So in general, we do not want to splice them together. Otherwise, we take the device off and there's no difference in the circuit because these wires are still touching. Okay, so that's what they're talking about when they're talking about electrical supervision. Again, there is a caveat to that, and we'll talk about that coming up here. And then it goes back into smoke alarms. Again, this would be the residential application where we have the detection and the alarm as part of one unit. So we don't have a fire alarm panel. These are used again in dwellings. Anything that doesn't need to be tied into a full system. So it does talk about that stuff again. Smoke detectors again, doesn't get into the exact of how they do it, but again, that was in the previous module. So these are going to be field devices or initiating devices in our system. These are going to change their state based on, again, whether it's smoke, heat, light, and then they're going to send a signal back to the panel, and then it's going to change based on that. Then it talks about fire pumps specifically, again, because there's code rules for it. So it talks about that you can have a service box for a fire pump that is a separate service box from the equipment, or we can actually have one that's a separate supply. Okay, so we have, here's our service or supply coming down in here, and we have a separate disconnect going to our fire pump. Here's our transfer switch that would transfer over from the supply to the emergency generator and to make sure this fire pump works still. And then we have one that's just a total separate service that it talks about here too. Okay, so those are the two different scenarios that they're going to talk about. Go through all the disconnecting means, overload. We don't need overload protection for that pump motor because we basically don't want it to trip on overload. We just want it to run as long as possible. So definitely go through that as well too. We don't need ground fault protection on a fire pump because we, again, don't want that to turn off. So definitely go through those code rules. Pretty straightforward. Then it starts talking about in objective 3 about field devices. So, and this is kind of how we're going to start wiring our fire alarms together. So a field device is a remote device in a fire alarm system that is electrically connected to a control unit. We have initiating, signaling, and supervisory. So initiating, basically it's just going to say is it normal or is there a fire condition? So that'd be your smoke detectors, heat detectors, pull stations, that kind of thing. Signaling device would be your warning, so that would be your beacons, your strobes, your horns. So here's all the signaling section, and this would be the initiating portion of it. So these are going to tell us we have an issue. Then the control panel is going to switch the polarity on the signaling devices, and then it's going to signal through there. And then the supervisory, It's for like a sprinkler system if it's fully operational. So again, if the valve has to be open for water to flow, that kind of stuff. So it's basically making sure that the system is ready. Those would be the other initiating devices that would potentially cause a change of state in the control panel. So it starts talking about non-addressable devices. So that's the first thing we'll talk about, are conventional. And we're going to hook them up into Class B or Class A. So in a conventional system, we have our control panel, we have our initiating devices. So this is a conventional system here, and our signaling devices. The big difference between a Class B and a Class A is on a Class B, we go through an end-of-line resistor. So you can see that here in the initiating circuit and in the signaling circuit. So we have current flow through all these devices through the end-of-line resistor and back to the panel. And that's going to give us a value of current that the panel is going to recognize as a normal condition. Now, if we have an opening, like so they talk about having a break where this X is, we basically have lost every device on this side of the X, or of the break. So only this device would be working at that point, and we would be in trouble because the end-of-line resistor wouldn't be in the circuit any longer. So we would know at the panel that that break had occurred. It just wouldn't be potentially very easy to find it. So you know there's a problem, but you don't know where the problem is potentially. So when we get into an alarm situation, we see these signaling devices have diodes in them. So during I guess under the normal condition, these diodes are reverse bias, so they don't conduct. Then what happens if we get into an alarm sequence, we see that the panel has changed the polarity. Okay, so what was normally negative here, positive here, during an alarm condition, so polarity of the voltage applied each terminal during normal conditions, and then they are again reversed for alarm conditions, and now we have current flow through the diode and then back to the panel. So it's not going to go through the end-of-line resistor, and it's going to actually activate this device. Again, as soon as these become forward biased, they're going to have current going through them and start signaling. So both of these would start signaling once the polarity is switched at the panel. So again, here we have a pull station that's been pulled. Now we have a path through the pull station, not through the end-of-line resistor anymore. So that's going to put the control panel into an alarm condition because there's a different value of current associated with that. We won't see the current that we saw going through the resistor. So we see in a condition, again, that could be through the smoke or heat detector, but in this case it's the pull station, so we have a path through there. Then that switches the polarity in the panel because it's an alarm condition, which forward biases these diodes and basically signals any device that's attached to that circuit. But again, big thing between Class B, it has an end-of-line resistor. Okay, and if we have a break, we lose everything on the other side of that break. So the other one we talk about is the Class A circuit, and it's very similar. They're run in parallel just like they do in Class B. The big thing is, and I'm sure you can see right away, is there is no end-of-line resistor. The loop actually goes right back all the way back to the panel. So there's an advantage to this, obviously disadvantages as well in regards to the wiring methods because you have to come all the way back to the panel again too. But the advantage is if we have a break here at this point, at point X, these devices will continue to work because they're backfed from the panel this way. So the fact that we have this loop back allows it, if there's a break, we could still have every device working even though we've lost a connection point. The same thing's going to happen in the signaling circuit. We're going to loop back to the panel. So we don't have any end-of-line resistors here either. So that's a Class A where we don't have, the end-of-line resistors. Now again, when we go into a signaling scenario where we actually want to, there has been a pull station or a detector that's been activated. The same thing's going to happen with the polarity in the signaling circuit. So here's what we would see in a normal state. So the polarity here is the same, but on our device signaling circuit here, this was negative, this was positive. Now this is positive and this is negative. So the panel switches the polarity that's going to the signaling device. Again, now these are forward biased, and this is working. So they even show that there's a break here, but each device is still working. Again, that's because it's backfed from the panel here, so now this device will continue to work even though there's a break here. Okay, so that's the huge advantage between A and B. So B has end-of-line resistors, A does not, it loops back to the panel. Okay, but A has that huge advantage of if we have a break, our devices still work and they are operational, which is obviously great for safety concerns. Then it talks about tamper switches. So there's portions of the fire alarm system that if it's got a sprinkler system, it'll have valves, it'll have potentially a sprinkler tree attached to it, all that kind of stuff. We have to know if that's operational. So a lot of these devices have tamper switches. So if you remove the cover, it opens this circuit. So as soon as that's open, now we have an open circuit, it's going to go into a trouble scenario. It's not going to alarm, but it's going to go into a trouble because we have a break in our circuit. So we're not going to be going through the end-of-line resistor. So even these water flow switches, or in this next one, they just show it as a control valve. Okay, either way, they have a tamper or they have an indicator if it's not operational. Think of it like that. So we have our control panel coming through here again, making sure the switch is closed, then we'll read through that end-of-line resistor. So same thing here with the control valve. Again, same scenario. If it's got a switch attached to the position of the control valve where it needs to be in the open position, if somebody walks up and tries to close it, there's going to be a supervisory alarm on that, and it's going to go back to the panel and let you know that that is not operational any longer. Addressable devices. The big thing with addressable devices is the benefit of knowing where the issue potentially is. So we can still have an A or B, they call them DCL or data communication line. What it is there's basically a wire that's going to each device, and it's this device, each one of them is talking back to the CPU constantly. So it's constantly saying, I'm here, I'm good, I'm ready to go. Okay, and it's sending that signal back all the time. If for some reason it's not ready to go, then we're going to get a trouble signal. The advantage to an addressable system is when I go and scroll through the display, I can actually see which device is the one that's having the issue. So as far as troubleshooting, this is a huge advantage, obviously. So we can still have our B circuit and our A again. A, we can see here's our loop back to the panel. But when these are all addressable, it's a huge advantage for troubleshooting, in my opinion. Again, a little bit more wiring on that, but this is, I would say, a smart system compared to a conventional system that's basically, especially a conventional B system that has end-of-line resistors, would probably be the most basic system. This is definitely more of the Cadillac, if you will, and a lot easier to maintain and troubleshoot and I guess make sure it's operational because it's constantly checking all the time. Again, we have some scenarios where we've talked about where we don't have, we're not allowed to do splices. We'll address that here coming up, because once we have an addressable scenario, it's a bit of a different situation. Because those devices are talking back all the time, we're not so worried about the opening of removing a device and the rest of it working. We'll go through that here coming up too. Then it starts talking about the different devices that we can attach to our system for pieces of equipment that don't have an address. So if we have an addressable system but we have a pump or a flow switch or even a signaling device that's not addressable, you can use those devices in an addressable system with supporting field devices. So they're monitor modules, signal modules, or control modules. And basically what it does is give an address to a piece of equipment in the system that doesn't have an address, so that the system knows that it's there and again can control it, or potentially just know on a supervisory issue, depending on what type of module. So the monitor module is one where we basically have an interface now between the CPU and the fire alarm system using these addressable systems, but with a non-addressable piece of equipment. So this is basically just going to give it an address so that we know if something's happened. And we have these in our lab too, so we're going to see examples of these. So basically it's just monitoring like a supervisory scenario in your system. So for a valve, for a fire pump, or for a fire system, for a sprinkler system, it needs to be open. We can use a addressable monitor module to make sure that that does stay open, and if it closes, send a signal back to the panel. So we can use those. So here's what it would be like. We would have our DCL cables coming in here, again, constantly reading, is this thing good? Yep, yep, yep. And then we have our field section where we come from the addressable monitor module out to the flow switch. And then we still have an end-of-line resistor here too, because this module is going to read this current coming back through here. And if there's a change of state, this module needs to know so that it can send that signal back to the panel. So we're still monitoring. If this tamper switch opens, this module is going to notice that and say, hey, my current has changed because I'm not going through the end-of-line resistor. And then it's going to send a signal back to the control panel saying, hey, we have a trouble scenario or a supervisory issue. Then we have addressable signal modules, pretty much the same kind of deal, except for now we're talking about signaling devices. So these are conventional devices that do not have an address, so we cannot address them specifically with the system. So we can use a signal module in order to help with that. Again, we run DCL cables from the panel, and we have potentially have a separate supply, a DC supply for that as well too. So these could be, again, regular horn strobes that aren't addressable, but now they are because we have this module. The control module, also think of it as a addressable relay. Again, same, we have our DCL cables coming in, and now we could have ancillary control of non-supervised equipment. So a fan and a duct, a door magnet, that kind of stuff. So when this addressable control module, when something happens, it can change the state of these contacts. So either open or close, again, whatever the original state was, and change the state of that contact so that it either de-energizes or energizes things on the event of an alarm. Okay, so that's kind of the three additional modules we're going to add potentially. And again, we do have these in our lab as well too. So the last thing kind of want to touch on here, this is under the addressable device fire alarm circuits. So they talk about a DCL-B, DCL-A, and DCL-C. So B, again, is similar to class B, but they don't have end-of-line resistors. So even if it's a DCL-B, if it's addressable, we don't have end-of-line resistors. So again, just make that distinction between a conventional class B or an addressable class B. If it's addressable, we don't necessarily have to have end-of-line resistors for our addressable devices. Now you can see they're still here on these signaling devices. That's because we're using conventional devices, detectors here or signals here, with a signal module or a monitor module. So we do need them here. But the devices that we saw that loop on a class B, we had them loop and into an end-of-line resistor. We don't have that in the DCL-B where we actually have addressable devices. We could have a DCL-A, again, that's where it comes back to the system. It's hard to say. I mean, to me, a DCL-B addressable system would have this very similar advantages to a DCL-A, where you could, if one of these devices isn't working, you'll know back at the panel, because the panel's constantly looking for that address, and if it's not there, it's going to go into trouble. Yeah, this is where, so this is in the module where it says we can, so we said in the code we don't want to tap, but this is where it says specifically DCL-B configurations allow for tap splices under certain or under specific conditions described by the manufacturer engineer. In DCL-B configuration, as in class B, any addressable devices beyond a break in the circuit wiring can lose the capability of reporting an alarm condition to the CPU. And then tap splices cannot be used in a DCL-A or DCL-C. DCL-C is basically just one that goes through more than one fire zone. Okay, that's the difference between DCL-A, B, and C. That's on page 31 of your mod. So DCL-B can be tapped in this specific scenario. So addressable class B potentially can be tapped, and we'll go through that in our lab as well too. Last thing I want to talk about is the fault isolation modules. This is for a DCLC circuit. Fault isolation modules are required to isolate zones if short circuits occur that prevent other zones from operating properly. So we kind of want to isolate exactly what they're used, the term, from one scenario causing an issue into another zone. So we can use single isolation modules between zones if they're on the same floor, two of them between zones if they're on different floors separated by fire separation, and on each side of the scene floor of fire separation. So one module is required at the start and one at the end of the part of the DC loop that is in that zone. And basically it's just going to keep those faults to the areas that they're in. We can address it, deal with it, but the other portion of the system is going to stay operational. So it's isolating those faults to the zone that they're in. Okay, so that's kind of the long and short of the wiring. There's obviously some very specific terms in there to make sure you have an understanding on, but read through that, do the questions, and this will definitely be reinforced in our lab because we will hook up a lot of these scenarios.